All right, so what we're going to do is label the periodic table with information that will help us for a while. At this point, we've learned metals, nonmetals, and metalloids. So you have a stair step. Anytime you hear me say something about the stair step, that's your stair step. And the metals are located on the left of the stair step. Metals are on the left of the stair step. Non-metals are on the right side of the stair step. So metals are located on the left, non-metals are on the right. The other thing that we have talked about with elements is their state, whether or not they are a solid, liquid, or gas. So I want to put a star on our two liquids. So I'm going to put a star, I'm going to come down here, a little legend, liquid. And we call it liquid at room temperature. Obviously, room temperature is relative to your room, but that's the general consensus, is that bromine and mercury are liquids at room temperature. I'm going to draw a slash line through all of the gases. Carbon is not a gas. Not a gas at room temperature. Say it again. Carbon is a solid at room temperature. Carbon is a solid at room temperature. Carbon is a solid. So anytime you see that slash, that means a gas at room temperature. Also put a note here, there are two liquids at room temperature. And there are 11 gases at room temperature. Obviously, the unmarked are what? Solid. The unmarked are solid. So anything that's not marked is a solid at room temperature. All right, another way that we can label our periodic table is whether or not they are a metal, non-metal, or a metalloid. That's another way. So we've already said metals, I've already said non-metals, but what I didn't talk about were our metalloids. Metalloids are located along the stair step, except for aluminum. Everybody that touches the stair step except aluminum is considered to be metalloid. So there are 8 metalloids. So everyone that touches the stair step except aluminum is a metalloid. So everything that I've done now labeling wise, those are the labels based on everything we've already talked about. So I've talked about metals, nonmetals, metalloids. I've talked about gases and liquids and solids at room temperature. We've talked about that last class period. Now there's another way we can classify elements, and that is to their family or group number, family name or group number, or their period. So you don't understand that until I tell you. Columns are called groups or families. The The columns are called groups or families. The rows are called periods. The columns are called groups or families, and the rows are called periods. Before I label those, I do need to clarify something that would be confusing to me if I were new to this. Where is hydrogen? What side? But what metal or non-metal side? It's on the metal side, but what is it really? It's a non-metal and it's a gas. So you may want to note to yourself, this is a non-metal. Hydrogen is a non-metal. It is located on the periodic table where it is located because it only has one valence electron, and that's going to be taught in a couple of weeks. Okay? It needs to stay where it is, but it is a nonmetal and it is a gas at room temperature. It has the ability to act like a metal in that it will transfer its electron and have a positive one charge, which is what you were learning in nomenclature. And so again, it's a unique element, bottom line. It's a very unique element, but it is a nonmetal and it is a gas at room temperature. Okay, so our columns, groups are family names, and our periods. Periods are easy. Periods, there's only 7. 1, 2, 3, 4, 5, 6, 7. Those are super easy, the periods. The columns have old names as well as new names. And they have Roman numeral names. So there's actually 3 ways to name the columns. That can be confusing. The easy way, I'll start at the bottom. The easy way is simply 1 through 18. These are the group numbers, and this is the newest way that we do them. 1, 2, 3, 4. Oops, I can't even count. Gracious. You can count. Can somebody turn that off, please? All right, so 1 through 18, those are group numbers. So what I could do on a test, I could simply ask you, and this is something I would spend some time doing, just sitting and reading your periodic table. I would just say, hey, what is the element in group 4, period 4? What is the name of the element? Titanium. Titanium. It's kind of like playing a puzzle, a real simple puzzle. Just basically, it's like reading a multiplication table, if you remember doing that, if you ever had one that you looked at. What is the symbol of the element in group 14, period 5? SN. What's the name? 10. Okay? So those are questions, just a simple question I could ask you. Okay? All right. Another naming of the families is the family name. Family names are the older names, and that's the oldest method of naming. And this is called the alkali metal family. This one is called the alkaline earth metal. So the alkali metal, the alkaline earth metal. All family names or all group names will call this section the transition metals. All of that middle section is called the transition metals. Boron, carbon, nitrogen, and oxygen just simply get called their family name with the who it is at the top. We don't really have specific family names for those, so I'll leave those off. Then we call this family the halogens, and this family the noble gases. So really there's only 4 family names that are really used much anymore, and that's the alkali metals, alkaline earth metals, halogens, and noble gases. I point these out because you've heard some of these names before. Where have you heard some of these names? Well, besides school. Besides school, where have you heard these names? In the real world, where have you heard 3 of those 4 names you have heard in the real world or something like them? Where have you heard something like those? Think about things you use. Electronics. Batteries. What have you heard about batteries? Alkaline batteries. Have you heard that before? What do you now think alkaline batteries probably have in them? Either one of the alkali metals or an alkaline earth metal, right? Would that make sense? So do you see where that's coming from? All right, there's another one. What is the other one you've heard in the real world? Maybe not. Maybe I'm assuming. Maybe you are too young to. Halogens. That's halogen what? Light bulbs. Halogen light bulbs. And again, I hesitate on that because now we're into LED light bulbs. But halogen light bulbs, so there was the normal incandescent light bulb. Then headlights on cars went to being halogen light bulbs. Halogen headlights. That's what you would have on your cars. Now we've gone to LEDs. And so, but halogen headlights would have what in them? One of the halogen gases. That's what they would have. They would have one of the halogen gases in them. Noble gases. That may be something you've not heard in the real world before, but you probably have heard it in class. What does it mean if somebody says noble? What do you think of when you think of nobility? In general, power. Kings, kingdoms, queens. That's what we're dealing with here. Are these elements kings and queens? No, but let me ask a question. Did any of you get invited to baby showers or weddings for any of the dukes or duchesses or queens? Did you go to the funerals or anything? You weren't invited. You weren't home. You could have gone, but you were invited, but you couldn't go, right? No, why not? Do they need us to be there? No offense, we are matter and we do matter, don't forget that. But do they really need us to be there? No, they don't need us to be there. So tell me about these noble gases. Tell me, Ryan.
They actually have like the most electrons before they actually get like a full ring, as in like the alkaline metals.
So do they need anybody else? No, the reason they're called noble gases is because they don't need to bond with anybody else. They have everything they need. And again, that's a precursor to what you're going to learn. But that's why they're called noble gases. So do they form compounds very readily? No. Noble gases do not form compounds very readily. And so that's, again, why they have their name. All right, the last way we name it, or the groups, is an old, called the Roman numeral North American method. But it's going to make sense later. I'm just going to have you label it now. It'll make more sense later. So you've got 1A, 2A, then you skip all the transition metals, 1A, 2A, and then these go across, 3A, 4A, 5A, 6A, 7A, that one you can't see very well, and then this is your 8A. Those of you that have had a chemistry class before, you know what that means. We're going to get there for the rest of us. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A.
is hydrogen an alkali metal?
Hydrogen rather is not an alkali metal. It's a non-metal, but it acts as a metal. So it stays here because of the number of electrons it has, which we're going to talk about later, but it truly is a non-metal. So it's a very unique element. It a lot of goofy things and good things, but it is a non-metal, but it acts as a metal. So that it is not an alkali metal really. And I won't ask you specifically what it is because it's an odd one. It's definitely odd. All right, questions on this? Okay, so now, charges. You wanted me to go ahead and show you charges since you didn't have me in lab? Sure, I can do that. We can talk charges. All right, for those of you that, my group yesterday, I had them label my periodic table. So in lab, you're doing nomenclature. So this column has a charge of +1. This entire column, when it becomes an ion with a +1 charge. Now, hydrogen can be -1 when it's with a metal, but for right now, we're going to just call it +1. I think most of your compounds will end up having it as a +1. This column, what charge does it have? +2. This entire column is +2. Very good. So this entire column is +2. This one's +1. Come over here to the zinc, cadmium, and mercury column. You may put a +2 above that column. The entire column has a +2 charge. However, I will warn you, there is a mercury 1 and a mercury 2, but both of them are +2. They both are +2, even though they have different symbols. Mercury 1 is Hg2, Hg subscript 2. Mercury 2 is Hg. Do you all have your ion sheets with you by chance? Probably not because they're from lab. Do you know what I'm talking about, the ion sheet from lab? Nope, some of you don't. Hold on a minute. Let's finish this and then I'll show you. Silver is +1. Label silver +1. Aluminum +3. Aluminum +3. Silver +1, aluminum +3. And then above your nitrogen family, -3, above oxygen, -2, and above your halogens, -1. All right, just keep it. In lab, if your instructor did not show you this, you have an ion sheet. Looks like this. Anybody seen that yet? If you have not seen it, it's on Blackboard. You need to go print this out on Blackboard if you have not seen it in lab. It is in your Blackboard, on your Blackboard site in lab. It's there. Why did I scribble through all this? Well, no, they are important. How did I give those to you? Look at everything you just labeled. Look at your periodic table that you just labeled. Look at hydrogen, lithium. In fact, I've got it highlighted right here beside it. Look over here to look at this column. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. What charge do they all have? +1. Look. Hydrogen, lithium, sodium, potassium, rubidium, cesium, and silver. What did we put for silver? +1. Have you just memorized this entire column by labeling that? So you don't have to memorize it. It's as long as you know how to label it. You will get a periodic table on your quiz in lab and in lecture. Always. +2. Look at the next column. Beryllium, magnesium, calcium, strontium, barium. Do you see all those? Boom, 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 right? +2. And what else did I tell you to label as +2? Zinc, cadmium, mercury. +2. Follow? plus 3 aluminum, and there it is, plus 3 aluminum. Hydride, hydrogen can be -1. Very seldom will you see it -1. I'm not saying just scratch it out like I did, but it's not something that you're going to see much. If you see hydrogen with a metal, in other words, if you see NaH, then sodium will be the +1 and hydrogen will be the -1, but it doesn't happen often, okay? So fluoride, chloride, bromide, iodide, fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, phosphide, boom, boom. Do you need to memorize this part if you know how to label your periodic table? No, that's why, okay? How many of you were told this in lab? Some of you, I know mine, how many weren't? Okay, all right, good. Okay, I'm not good that you weren't told, but it's okay. Now you're told, okay? This should help with nomenclature. All right, now, that will help you. When I say to you, and I'm going to come back to ions, this sounds so corny. I know you think I'm just a crazy woman, and I am, but that's okay. When you have this periodic table labeled, make a copy of it. And when I say make a copy, I don't mean go to a copy machine. I mean handwrite another copy of it. The more you handwrite this, the better you will memorize it. The other thing I want you to do is study it. Now that sounds corny. I'm not saying magnesium, 24.305 a mass, it's atomic number 12, and the electronegativity is 1.31. I don't mean any of that. I mean magnesium. And literally talk to yourself. Magnesium, it's a metal, it's in period 3, it's in group 2 or 2A, it's an alkaline earth metal, it has a charge of +2 when it's an ion. Just close your eyes. Point. Oh, aluminum. Do the same thing again. Do the same thing again. Do you see what I'm saying? Why do I say that? You may know why I say that. What good will this do you? So that one, you know, but more than just knowing how, I'm never going to ask you to label a periodic table again. What are you, okay. If you learn your ion, or if you learn your conversion factors, for those of you that have learned your conversion factors, what have you discovered about dimensional analysis? It saves time and it's easier, right? If you don't learn your ion or your conversion factors, is dimensional analysis hard? Some of you don't have a clue because you haven't learned your conversion factors. Same thing here. You can see where things are on your periodic table. What have I told you? Every time you're going to have what? Every quiz, every test, you're going to have what? So if you spend time looking at this periodic table, what is that going to help you with? When you get it in front of you again, are you going to be able to visualize it better? That's why I'm saying do this. And if you know these charges, is that going to help you with nomenclature? Yes. Yes, it's going to help you with nomenclature. Now, the other thing that you need to start memorizing, and this should have been mentioned in lab. If it wasn't, it might be on your syllabus. I know in my class it was mentioned. The bottom part of this ion sheet are your polyatomic ions. You have to start memorizing these. You have to start memorizing these. Now, I'm not going to go through all the tricks right now and the hints because I don't have time, but you have this video on YouTube this afternoon. Fast forward it to this page and copy down these notes. Okay? These are your tricks to helping you memorize this. Chunk them like I've chunked them. All 8s and ites have oxygen. All 8s have one more oxygen than their ite with the same charge. If hydrogen is added to a polyatomic ion, the charge is changed by +1. Why? Because hydrogen has a +1. If you'll study this, learn these, it will make more sense to you in how to study these, and it saves you time. Okay? On the back side, you have the transition metal ions. They also have tricks. Obviously, the Roman numerals first of all, they're metals, so they're all positive. The Roman numeral is equal to the positive charge, so don't ever mess that up. And the the us ending and the ick ending indicate the charge. So if it's an us, it's going to be a lower positive charge. If it's an ick, it's going to be a higher positive charge. Again, go back and look at these. You have to know these. You have to start studying these, okay? So spend some time with your ions. Spend some time. I know that you all are overloaded right now as far as lab and lecture are concerned. You're probably feeling a lot of stress and pressure because it's like, man, they just loaded us up with a whole lot of stuff here at the beginning of the semester. But I will promise you, if you will learn it now, the rest of your semester will be so much easier. Tell me, typically, let me just ask, maybe you're not like me, but many of you are. Would you prefer to be inside studying when it's cold and wet and rainy, or when it's nice and sunny in the springtime? When would you rather be inside? Now? Come March, when it's 70 degrees outside and sunny, are you going to want to sit inside and learn all this junk? No, you're going to want to be outside. So I'm pushing you now so that you can be more free later. If you don't push yourself now, you will fail. Okay? You may fail. I won't say you will fail. You may fail. I understand. C for, that's all you got to get. But why settle for a C when you can do better? Okay? You can do this. All right, let's get going now on mixtures because, again, this is next week's lab. So hopefully you're starting to see the correlation. So let's talk more about mixtures. Okay, so we had distillation, filtration, a sieve or sifting, magnetism. I want to talk real quick about magnetism again. What industry, and it's not necessarily the most glamorous industry, definitely makes money, but what industry uses the concept of magnetism to separate mixtures? Say it again? The dump. Recycling centers. What do? Can you make more money off of aluminum recycling than you can steel? How can they separate aluminum and steel? With a magnet. What is the magnet going to pull up?
Steel.
The steel. Anything that contains what? Iron. Is it going to touch aluminum? No. If you've ever taken off, I'm a scrapper, man. I take scrap off, buddy. I can make some $5 off scrap. It's $5 I didn't have, Clean up the farm, take off some scrap. I got buckets I need to take off now. So I'm not good about separating it out, though. But when I get there, oftentimes they'll help me out. I know the aluminum, and I'll separate that out. But they'll go through, and they'll take their magnet when they're going through my little buckets sometimes and see if it's got any aluminum or not in it and separate it out. And that's what they do. Now, is that a glamorous job? No. But they're using the concept. Do they make money? Yes, they make money. And so that is a real life way to separate a mixture. Now, that's a mixture you probably never thought of. You never thought of the dump as being a mixture. Now, the other thing that maybe you've never thought of before, how do we get, are any of you near Newburgh, Indiana? What's in Newburgh that deals with aluminum?
It's called Kaiser.
Kaiser or Alcoa. There's a big, and do you know about what happened? Do your parents work there? They had a silo that dropped this week, and they're down. It fell. So in Newburgh, Indiana, there's a plant that smelts aluminum. Their company, the whole global company, mines bauxite, which is a mineral that is aluminum containing, and then they basically, now this is all of this together. Bauxite comes out of the ground. It contains aluminum. It's a rock. You have an aluminum can that came from that bauxite originally. How in the world did it get from rock to can? Not just melting. We had to, is that rock considered a mixture? And it's a mixture of compounds as well as elements. So how do we get that separated out? How would we get that separated out? Well, potentially some sifting and sieving maybe at the very beginning to get the actual bauxite out, but we don't even have it on here yet, the one that you're going to need. A magnet's not going to get aluminum, so it's not, and you couldn't separate it out. The magnet's not going to be strong enough to pull, and plus it's in a compound form in the rock. Now, something that I call selective solubility. I call it that. It's really called solubility extraction. Selective solubility. Solubility extraction. Could there be a chemical that would dissolve the aluminum compound in the bauxite, but it would not dissolve the granite, the silicon, whatever else is in there? Could there be? Yes, there is. Have any of you ever picked up geodes? Anybody ever picked up geodes and quartz on your farm maybe? You know what I'm talking about? I did not know this until more recently because I was just doing some research one day. Have any of you ever cleaned them? Maybe you know this already. Have any of you, how did you clean them?
Water.
You've just cleaned them with water. Has anybody ever used anything else to clean them? If you put those in, there's two different things, and you can do this, you can Google this yourself. But if you put those in hydrochloric acid, which you can buy, it's called muriatic acid at Lowe's. If you put those in muriatic acid, or if you put them in ironite, and I haven't looked up to see what the chemical is in ironite, but if you put those in that, guess what happens? The hydrochloric acid will dissolve the junk, but not the quartz. So what you get back out is this really, really pretty piece of quartz that's clean with all the junk off of it. So that same concept, you take the bauxite, and I don't know what the chemical is. It might be hydrochloric acid, I don't know. But you put it in the, let's say that bauxite, let's say that the aluminum compound will dissolve in hydrochloric acid, but the quartz will not. So if we put that bauxite in hydrochloric acid, what's going to be dissolved? The aluminum compound, you with me? So now, did we just extract the aluminum compound from the rock? So was that solubility extraction? Was that selective solubilities? It dissolved one thing but didn't dissolve the other. Now we have in the liquid aluminum compound with the other chemical, maybe hydrochloric acid. Now what can we do? What can we do now? Tell me, what process is that? What's it called on the words? We could distill it. Can we distill it? Now, if we distill it, we're going to get, we don't know for sure, and again, we're making this up, so we don't know what gas is going to come off. But we could distill it or simply evaporate it, and then there's going to be a solid left. What's the solid going to be? The aluminum compound. But we still have to find a way to just get the aluminum out completely by itself. So are you going to have to find another chemical reaction that will either react with the aluminum and kick the aluminum out, which is what we're going to learn later in this year. We're going to learn about reactions, a single displacement reaction where you put an element with a compound and it kicks the other element out. So our goal is to get what by itself? Aluminum by itself. So chemistry is involved from the beginning to the end, and much of it is not just chemistry, it's physically separating a what? A mixture, because that's how it starts. That's how it starts. It starts with separating a mixture. So selective solubilities. Selective solubility or solubility extraction can actually be used for either homogeneous or heterogeneous. In the case of our rock scenario, would that be hetero or homo? That rock would be a heterogeneous rock. If you've ever seen rocks much, they're not necessarily the same throughout. Now limestone is, but we're not talking about limestone. So it would be a heterogeneous. And here's what happens. And I'm just going to make a note here for you to remember. One substance, and I'm not going to call it a substance because it may not be a substance by definition. One thing, I'm going to say thing in general here, one thing dissolves in the solvent, others do not. One thing would dissolve in the solvent, but the others would not. Give you another little scenario here, and I'm going to make a note of this just so that you have this for your notes. Then we're going to have one more here. If I gave you a mixture of white sand, sugar, so if I gave you a mixture of white sand and sugar, so I gave you a white sand and sugar mixture, tell me how to dissolve it. Or, I'm sorry, shoot, gosh, I always do that.
Put it in water.
Man, why do I do that every time? I always say the answer. How you separate is what I meant to say. You would what?
Put it in water.
Put it in water. And then, what would you do after you, why did you put it in water? The sugar will dissolve in the water, but the sand will not. Then what do? I want all parts. Then what would you do? Filter it. Then you would filter it. And what's going to be left in your filter paper? Nuh-uh. Sand. Sand would be left in your filter paper. What would be the water part? Sugar water. So have you separated out the sugar water with the sand? So you have the sand out. I want to have the salt and the sand separated. How do you get the sugar separated out from the water? You could distill it if you wanted the water. If you didn't care about getting the water back, you would just simply evaporate. You would simply evaporate it. And then in your evaporating dish, what would be left? Sugar. What would be over here in the filter paper? Sand. Does that make sense? Is that solubility extraction? Did you get that? Remember that. Because you're going to do something like this in lab, not next week, but the following week. Okay? You're going to be doing something like that. So remember this. Guys, think about real life. Think about things that are done like this. Whether it's in industry, some of you are manufacturing engineering technology. That's your major. Do you realize that your major would do what the Alcoa company does? That's manufacturing engineering technology. That's part of it. Being able to think through these steps. It's not just going to be somebody telling you exactly what to do. You got to think. And this is helpful for that. All right, next week's lab. Haven't gotten to that one yet, but it's going to be last here. Chromatography. Chromatography is a method of separating mixtures. It's the prettiest method, I will say. Can be the prettiest, depending on what you're separating. I think you're going to find it pretty next week. Maybe pretty, if you call it pretty. It's colorful. Maybe I should say that. It's colorful, okay? Where's the word color? Do you see anywhere in there that's color? Chroma? Okay, if you're familiar with words. All right, so chromatography. I'm going to just write and then I'm going to explain. It has a stationary phase, and mobile phase. And is based on the attraction each has for the other. It will only be used for homogeneous mixtures. So it has a stationary phase and a mobile phase and is based on the attraction that each has for the other. Seeing if I could actually show you something in real life, but I'm not going to be able to because it's not, this paper is not working. Have any of you ever had, and this is obviously some permanent ink on this one. Have any of you though ever had a piece of notebook paper, and I just threw some water on this. Have any of you ever had a piece of notebook paper though, and it got wet, and you started seeing the blue and red lines run? That's chromatography. That's chromatography, okay? So, you've seen it? Coffee filters. Coffee filters. So you've done this. Yes, that's exactly right. Coffee filters. Coffee filters, same way. We could take a piece of toilet paper here. If I take a piece of, this is the clean part, just so you know. If I take a piece of toilet paper, and I don't know if this is a permanent marker or not, or a permanent pen or not, but we'll see here. So if I take a piece of toilet paper there, and it looks like it's, once again, we got some permanent ink going on around this place. I don't think this will work either. Probably not going to work. We got too much permanent ink around here. I don't have a good solvent, but here, I got a solvent. Maybe. Maybe not. But this is all good because, put those up there. So the whole concept of chromatography is you have a mobile phase. On the paper, my mobile phase was water, or no. On the paper, my mobile phase was the expo cleaner. On the toilet paper, my mobile phase was water. And then I had something I wanted to separate. What's the something I'm trying to separate? The ink. I'm trying to separate the ink. And I have a terrible, I say a terrible experiment. I can't say it's terrible. It's just an unworking experiment. Because obviously either my stationary phase is not appropriate for my separation, or my mobile phase was not appropriate. Does that make sense? So in other words, what I've discovered is this, and it may not even have, I'm not even sure if it's got anything in there that's right. Usually this is an alcohol based, and I'm not smelling alcohol, so I'm not sure if that's even alcohol based or not. But typically what will happen when you do, what you can have happen, or what you can see, if these were water-based on this tissue, on the water-based one, if this was water-based, then what you would see, and you've seen it with coffee filters, you add water to a water-based marker, and what's it start to do? Run, spread. So what's happening is the attraction for the mobile phase to the stationary phase. So in our case, water, be with me guys, get off your watches. In my case, the water is the mobile phase, the tissue is the stationary phase, and the water is spreading, so the water has an attraction to the stationary phase because it's obviously gotten bigger, right? But did it dissolve? Do I have a selective solubility with my ink? Do you see how these go together? What do I not have? I don't have anything that will dissolve my ink, right? So in chromatography, you have to have something that will dissolve your substance, and then depending upon the attraction for the substance you're trying to dissolve to its stationary phase, will cause it to move so far. So in lab next week, it's called thin layer chromatography. Now listen to me carefully so you're not messing up lab next week. This lab is not in your lab manual. This is all labs. You have the lab to do, the pre-lab you do out of your lab manual. But the actual experiment is a blackboard paper handout. You have to print that out. So you're going to do the printout from lab, but your actual pre-lab you do from your lab manual. And what you're going to use, and I'm holding my finger here, they're little rectangle pieces of thin layer chromatography paper. It's actually not paper, it's a silica gel on a plastic sheet. And you're going to be separating food coloring. So you're going to be dotting food coloring onto the chromatography layer or chromatography sheet, sticking it in a solvent, which is an alcohol-based solvent, and then over time you're going to start to see the separation of those food colors. And then you're going to be taking purple Kool-Aid as your unknown, because what do you think the purple Kool-Aid colors would have in it? Come on, what makes purple? Red and blue? So guess what colors you're going to be testing? What are your known colors going to be? A red and a blue. I think it's 2 reds and a blue. And so you're going to be checking which of those are in the purple Kool-Aid. And how do you check those? Because you check them, if this red line matches up with the unknown, then that means that's the same red food coloring. And then you're going to calculate some values with numbers, etc. That's chromatography though. You've done it with coffee filters. In school, you might have done this, and you never might have called it chromatography. This could have been an art project you did. You could have done this in an art class. Any of you ever do it on a t-shirt? Have any of you ever tie-dyed? Tie-dyed is similar, but a little different. Tie-dyeing is similar, but you still have the running of colors in tie-dye, okay? So, how do we separate mixtures? Or is there just one way to separate a mixture? That's an easy answer. Is there only one way to separate mixtures? No, there's lots of ways. You need to know these, okay? You need to know and be able to use them. All right, keep going on elements. Gonna move a little faster now. Wanted you to get that all in good, and I've done a whole lot of lab stuff today. Didn't expect it. So, distribution of elements. We've talked about recycling a little bit. This goes along with that. What is the earth made up of? This is the earth's crust, sea, water, and air. What's the number one element? Oxygen. Now, where is all that oxygen in the earth's crust, sea, water, and air? Where's all that oxygen? Air. That's not true. It's there. Where? Ocean. It's in the water. What is water?
H2O.
Hey, Buddy Rowe, are you on your phone back there? Uh-huh. Yeah, yeah. Put it up. All the way up. Thank you for being honest. All the way up. Okay? It's in all the water. It's in all the water. What's the formula for water? H2O. If there are 2 atoms of hydrogen for every 1 atom of oxygen, then why do we say that it's because of the water? You may know. I haven't taught that yet. You may know though. If there's 2 atoms of hydrogen and with every 1 atom of oxygen making up water, then why do I say because of the water it's more oxygen? Look at your periodic table. See if you can figure it out. Say it.
Oh, it's A equals alpha, isn't it? Or no?
You're thinking of ions. We're not talking about ions. I'm saying water is H2O, so it's actually 2 atoms of hydrogen to every 1 atom of oxygen, but I'm saying that the oxygen is what makes, why is the oxygen so great? What makes the oxygen so great in water? Wake up over there, buddy. It's mass. It's mass. Look at the mass on your periodic table of oxygen. What is it? 16. What's the mass of hydrogen? 1. It's because of the mass. And so oxygen is mainly due to the water. Oxygen is mainly due to the water. Stay off your phone, okay? Yeah. You keep getting in your pocket, dude. All right, so it's mainly the oxygen in the water. What else is it? Silicon. Have you had soil science yet, some of you? Have you had a geology class, some of you? Tell me where's silicon? What's silicon making up on the earth? Do you know? Silicon, what's silicon making up? You like to go play in it. Sand. 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 Do we have a lot of sand in our soil? So that's where the silicon is. And then aluminum. So why is it important to recycle aluminum if it's so abundant? Maybe I explained it just in my example of talking about bauxite. Is it a whole lot of trouble to go mine the ore and do all that rather than take an aluminum can, melt it down, clean it up a little bit and recycle it? It's a lot easier to melt it and clean it up and recycle it than it is to go dig and do all that other stuff. So you need to know those top three. I don't care about the rest of them. This is just interesting. You need to know the top three. You especially need to know oxygen's the most abundant in the human body. You need to know these. CHON. You're made up of CHON mainly. What's CHON? Carbon, hydrogen, oxygen, and nitrogen. But who's number one? Oxygen. Once again, why is oxygen number one? Water. What are we mainly? Water. We are mainly water, and we're a lot of oxygen. It's not because of our lungs, it's because of the water. It's because of the water. So it's pretty cool. Both places, what's the most abundant? Oxygen. And the oxygen comes from what? The water. When you hear maybe old sci-fi stuff, new sci-fi stuff, whatever, what are they always looking for? And not just sci-fi. What do you have to have in order for life to survive? Water. Water. And that, I mean, it's pretty true. We have to have water. You're going to die much faster of dehydration than you will without food. All right, so we're still classifying matter. We're still going through and classifying matter. And so the last thing we're going to do with classifying matter in class today is learn our diatomic elements. The diatomic elements are the following 7 elements. Hofbrinkel. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Hofbrinkel. It's a goofy name. Some of you may have learned it as Brinkelhoff. Either way, if you'll learn the acronym Hofbrinkel or Brinkelhoff, it will make things much easier for you. What are the diatomic elements? The diatomic elements are 7 elements, and I'm even going to make a note here. I'll give you several ways to memorize them. There are 7 elements. Make a 7 on the periodic table, and I'll show you that in a minute. They do not exist alone in nature. They must be in diatomic state or combined with other elements in a compound. They do not exist alone in nature. They must be in a diatomic state or combined with other elements in a compound. They are stable as diatomic elements. They are unstable as monatomic. That means with only one atom by itself, they are not stable. They cannot exist without being combined. Look at your periodic table. find nitrogen. What number is nitrogen? 7. That's the helpful thing. If you just remember 7. Find nitrogen and make the number 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Do you see that? It makes a 7, and the 7th one it's pointed to over on the left, which is hydrogen. So that's just another way to remember it. It starts at 7, it makes a 7, it's pointing to the 7th one, which is hydrogen, or remember Hofbrinkel, either way. So who are they? I've already told you, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. How are they written? If they are alone, they will be written in the diatomic state. H2, O2, F2, Br2, I2, N2, Cl2. They will always be two nonmetals bonded together. They cannot exist alone. Where have you heard this before? Not all of these, but one of these. There's one of these that you knew this about without maybe knowing why. Not water and carbon dioxide. In fact, I'm going to specifically talk about those. Those are compounds. Which one of these have you heard called this name before? Not diatomic. I'm saying, say these. H2, O2, F2, Br2, I2, N2, Cl2. Where have you heard one of those before? O2. You've heard O2. Have you ever heard anybody say, give them some O? What do they say? Give them some O2 or oxygen. They don't say give them some O. Why not? You can't give them O. Why not? O can't be O. You can't just have O. Now, you made the comment water and carbon dioxide. So here's my question. Water is H2O. Water is H2O. Is it H2O because H is diatomic? Or is it H2O because that's what makes water? Based on what I've said, in order for these to exist, they have to be either diatomically bonded or in a compound. What is water? It's a compound, isn't it? So, H2O, the H's are not even bonded together. This is H2O. This is what H2O looks like. H bonded to O, bonded to H. H, O, H is what H2O really is. It's HOH. Now, H2 looks like that. If I were to draw, what does H2 look like? It's that, H bonded to H. But H2O is this. So is this one diatomic or this diatomic? No, H2 is diatomic. This is the diatomic molecule. This is a compound. So this is the water compound. This is the diatomic hydrogen molecule. Guys, this is chemistry, okay? This is trying to show you some chemistry here. So this is the water compound. This is the diatomic hydrogen molecule. Now, we're not going to be doing this yet. This is to come after you understand more about compounds. But this is where I'm going, okay? All right, you need to, before you come back for next Tuesday, you need to print out set 4 notes. Make sure that you have printed out set 4 notes because we will work on those and finish these up on Tuesday, okay? Don't forget your homework. Thank you. Did everybody get the sign-in sheet?